Welcome back, Design Junkies, to Mechanical Engineering Made Simple.
We're diving deep today. And our mission is a big one. We really want to unlock the foundational mathematics, the core concepts of mechanics that really underpin all successful mechanical design.
Yeah, and this is for you, the listener. We're aiming to show why engineers trust these specific tools, these calculations, from abstract algebra all the way to real-world dynamics.
Trust is exactly the right word, because
Yeah.
if you look at modern engineering, it's all computational fluid dynamics, finite element analysis.
Right, this incredibly complex software.
Exactly. But that software is only as good, only as reliable as the math it's built on. And our materials today show this just incredible shift in the tools over time.
It's a huge contrast.
Yeah.
You start with what now seems like, obsolete technology.
Oh, for sure. Like the old school Kuffel and Esser slide rule. A marvel for its time, but it's all based on a manual logarithmic process. Very easy to make a mistake.
And you put that K&E slide rule, which took so much focus just to avoid a gross error, next to a modern programmable calculator, something like a Texas Instruments TI-85 or an HP 48G.
It's not even a fair fight. It's not just a leap in speed. It's a total revolution in precision.
So what was the point? Why make that jump?
Well, the whole purpose of embracing that digital power was to move beyond those error-prone procedures. Before these tools, every single calculation was this cumbersome, tedious exercise. The power of modern handheld calculation is that it simplifies these hugely complex steps while at the same time cranking up our precision. And that, in turn, is what allows us to trust the final design.
Okay, so let's unpack that foundation of trust. We have to look at the invisible engine, the thing driving all those equations we see in engineering handbooks.
The ones for beams, shafts, fluid flow, all of them.
Yeah. Those simple-looking rules, they were derived by mathematicians using calculus, using other advanced procedures.
Absolutely. At the very bedrock of modern mechanics is differential calculus, and specifically the derivative.
For those of us who maybe haven't touched a math textbook in a while, what's the core insight of the derivative for an engineer?
Simply put, the derivative is the rate of change of a function. That's it. It is the most powerful tool we have for analysis, for optimization. For a mechanical engineer, it really boils down to two key interpretations.
Okay.
First, it tells you the slope of a continuous curve at one specific point. This is how we understand how quickly a design dimension is changing.
So if you were trying to find, say, the weakest point on a curve or the most efficient point, the derivative shows you where that slope is at a maximum or minimum.
Precisely. The second key interpretation is velocity and acceleration. If distance, which we can call s, is a function of time, t, then the first derivative of that function, s of t, gives you the velocity.
And if you take the derivative again?
The second derivative, right. The derivative of the velocity function gives you acceleration.
That makes the physics connection really clear. Our notes actually have the equation for a body falling to Earth if you ignore air resistance. S over time, t equals k, multiplied by t squared. And here k is 16 feet per second squared.
Right. And now if you take the second derivative of that function, you land squarely on the constant for acceleration due to gravity.
32 feet per second squared.
32. Or the value engineers rely on for standard practice, which is 32.16 feet per second squared. That little difference, that 0.16, that's the difference between a textbook physics problem and a real-world engineering calculation.
So the derivative is all about the rate of change. Then the integral, the antiderivative.
Right.
It has to be about accumulation, right?
It is. Integrals are the language of accumulation. We use definite integrals, which are defined by the fundamental theorem of calculus. The integral of a function f of x from point A to point B is just the antiderivative at B minus the antiderivative at A.
That sounds very abstract. Where's an engineer actually using that on a design?
Oh, everywhere. Especially when you're trying to figure out physical quantities of weirdly shaped objects. Think about calculating the area under a parabolic curve, for instance. Let's say the equation is x equals y squared plus 1. If you need the exact area projected to the y-axis between, say, y equals -2 and y equals 2, integration is really the only practical way to do it.
And without calculus, you'd be what? Drawing a million tiny rectangles and adding them up by hand?
Which is basically what the integral does for you, just instantly.
Yeah.
And that integration gives us a precise answer, 9.33 3 square units. You use the same idea for volumes, centroids, and controid. This is a big one we'll get to later.
Yeah.
Moments of inertia.
Okay, moving past calculus for a second. Our notes also point to some specialized algebra that's still fundamental. I'm curious about complex numbers. They always felt a little like a mathematician's trick with that imaginary unit IR.
It feels like a trick, but it's a necessary one. Especially in electromechanical systems and vibration analysis, we have to rely on that imaginary unit I where I squared equals -1. Real numbers, they only tell you magnitude.
But complex numbers do more.
They convey phase and magnitude at the same time. When you're plotting the behavior of a spinning shaft or analyzing a vibration, you need to map not just how big it is, but its direction.
So how does that look in a design?
That's where we use the polar form. A plus bi equals r times the quantity cosine theta plus I sine theta. That r gives you the magnitude and theta gives you the direction, the phase shift. It's essential for making sure any rotating mechanism is stable.
And one last quick but important bit of algebra. Logarithms.
Yeah.
Even with all our computers, they're still really efficient for solving compound rate problems.
Oh, absolutely. The notes have a great example. Say a company's employment is growing at 15% per year. How long until the number of employees triples?
You can guess.
Or you use logarithms. The time n is just log of 3 divided by log of 1.15, and it comes out to 7.86 years. It's just a very elegant way to handle growth and decay.
So now we jump from the abstract math to the science of applying it. Engineering mechanics. This is where the numbers really meet the machine, and it's split into statics and dynamics.
Right. Statics is the study of bodies in equilibrium. That means they're either totally at rest or moving at a constant uniform motion, no acceleration.
And dynamics, then, is the opposite.
It is. Dynamics is the study of bodies that are not in equilibrium. So they're speeding up, slowing down, changing direction.
But both of them rely on the same basic ideas of force, specifically moment and torque.
They do. A moment is just a force multiplied by its moment arm. That's the perpendicular distance from the force to the pivot point. Torque is, well, it's the technical term for a force's tendency to cause rotation.
They seem very similar.
They are. The context is usually what separates them. We tend to say torque when we're talking about rotational work, like what an engine produces.
Okay, before we get into the calculations, we have to address something that causes huge confusion. The difference between the U.S. customary system and the SI system, specifically with mass and force.
Oh, this is more than just a naming issue. It is a philosophical difference that has led to actual catastrophic failures. The U.S. system derives mass from force. The standard unit of mass is the slug.
The slug, not something you hear every day.
No. And it's defined as weight, W, divided by gravity, G, which is 32.2 feet per second squared. The real problem, though, is that the term pound gets used for everything.
Pound force and pound mass.
Exactly. And they are not the same thing. If you mix those up in a critical calculation, you can be off by a factor of 32. It's a huge source of error.
And the SI system is much cleaner.
It is so much cleaner. It's elegant. The SI system derives force from mass. The kilogram is mass, period. The Newton is force, period. 150 kilogram mass exerts a force of m times g Newton. So 150 times 9.81, it's 1,471.5 newtons.
No confusion.
No confusion. Keeping them distinct is absolutely non-negotiable for safety.
So when we're analyzing a static system, say a simple supported beam, we're looking for equilibrium. What are the rules that guarantee it's stable?
There are two main conditions. First, the resultant of all forces acting on the body has to be zero. No net push, no net pull. Second, the algebraic sum of all the moments of all forces about any point you choose also has to be zero. That guarantees it won't rotate.
And to check those conditions, engineers are always breaking down forces that are at an angle into simpler components.
That's called force resolution. You break the force down along the x and y axis. So the force in the x direction, F sub x, is just the total force, F times the cosine of the angle phi. And F sub y is F times the sine of phi. It just turns a tricky geometry problem into a simple right triangle problem.
Let's use the classic example from our notes. A supported beam with a few different loads pushing down on it, 2 pounds, 3 pounds, and 25 pounds. And there's an upward support force, F, that we need to find.
Yep. And the fastest way to solve this is to use that second condition of equilibrium. We take the algebraic sum of the moments about that fixed pivot point, point A, and we set that sum to zero.
So you calculate the moment from the 2-pound load, the 3-pound load, the 25-pound load, and balance them against the moment from our unknown force, F.
Using the specific distances from the diagram, yes. And when you work out the simple algebra,
The support force F has to be exactly 221.14 pounds to keep the whole thing in equilibrium. That moment calculation is what ensures it doesn't pivot.
it's a perfect, simple illustration of how we use that math to guarantee physical stability.
And now we enter the world of dynamics, where things are moving, accelerating. And this is where the idea of inertia becomes so important. We need to talk about moments of inertia.
Right, which is just the term for a body's resistance to rotational change. And they come in two main flavors, both derived from the product of little elementary bits of mass or area and the square of their distance from an axis.
Okay, first up is the polar moment of inertia of areas, I sub PA.
This one is for plane areas. Think cross-sections of beams or columns. It's about how resistant the shape is to twisting. You just sum the moments about the x and y axis.
But for things in motion, the one we really care about is the polar moment of inertia of masses, I sub PM.
That's the one. I sub PM is used in all dynamics equations involving rotation. It's what tells you how much effort it takes to start spinning a flywheel or how hard it is to stop it. The units in SI are kilogram meter squared.
A lot of times, in a real machine, a part isn't spinning right around its own center of gravity. That's where the parallel axis theorem is used, right?
It is absolutely vital. The theorem, or what we call the transfer of axes, lets you accurately shift your calculation. You can move from the component's own center of gravity axis, call it z prime, to the main axis it's actually rotating around, zz.
And the formula for that is I sub PM equals I prime sub PM plus S squared times M.
Right, and that S is the distance between the two axes, and M is the mass. You have to account for that offset. If you don't, your calculation for rotational resistance will be completely wrong.
Okay. And this is where it all comes together. This is where all this abstract math gets connected to a real complex industrial product. Our case study, the design analysis of a high-power electrical vacuum interrupter switch.
This is the aha moment. This example shows exactly why we do all this, and it embodies a critical design philosophy. Function have to be the primary goal. It comes before costing, before tooling.
Because if you prioritize cost first,
You risk product failure. And on a high-power switch like this, failure is not an option. So the designer focuses the analysis only on the most critical elements where a failure could happen.
so we're talking about calculating the energy in the power springs, the forces on the crank arm, the torque on the main power shaft.
Yes, and even the current carrying ability of the copper blades. But let's focus on the energy comparison calculation because that's the ultimate validation.
Okay, what's the comparison?
This mechanism works by converting the potential energy stored in some big power springs into the kinetic energy of rotation in 6 heavy copper blades. We just compare the input energy to the output energy.
So, start with the input, the potential energy, E sub P.
Right. We use the spring potential energy equation, R sub S times S squared divided by 2. We calculate that for the 3 main springs in the mechanism, we sum them up, and the total input energy is 11,175 inch-pounds.
That's the fuel. Now for the output, the kinetic energy of rotation, E sub Kr.
And for that, we use the inertia concept we just discussed, I sub PM times omega squared divided by 2. We take the mass moment of inertia for those 6 blades and their angular velocity, which was calculated to be 27.1 radians per second.
And the total output kinetic energy is?
1,128 inch-pounds.
So 11,175 inch-pounds went in and 1,128 inch-pounds came out.
Exactly. The math validates the physical reality. There's a reduction in energy of exactly 4%.
And that's not an error in the math.
No, that small loss is realistically and predictably attributed to friction in the mechanism. This systematic calculation, rooted in calculus and dynamics, proves the mechanism is reliable and efficient before they ever build the expensive final version.
That, for me, is the absolute core power of engineering. You're taking these complex, invisible forces and making a 4% friction loss a predictable mathematical result. It's not a guess you have to fix with expensive trial and error.
We've seen how calculus gives us the principles, how statics ensures stability, and how dynamics, with moments of inertia, predicts precise motion. It all feeds back to that idea of trust in the numbers.
So what does all this predictability suggest for the world around us?
Well, our source materials mention Newton's laws of motion, specifically that a particle's acceleration is proportional to the resultant force acting on it. And when we look at that complex switch, or really any machine, we take that resultant force for granted. It's not one push or one pull.
It's the sum of everything.
It's the algebraic sum of hundreds of forces and moments that determines if a system is stable, how fast it goes, if it's safe. So I'd ask you to think about this. How often do we rely on these unseen mathematical checks? What other essential geometric or algebraic concepts, like trigonometry's Moll-White equation for checking triangles or using determinants to solve force systems, what other checks are providing this critical, unseen safety net in the world we all live in?
Fascinating thought. That predictability is what lets us trust the buildings we're in and the machines we use every day. If you want to dive deeper into the math and the mechanics we covered, definitely check out the bibliographical references listed in our sources for some further study.